atmospheric sounding. Dr. A. Chandrasekar obtained his BSc in physics from University of Madras, MSc in meteorology from Cochin University, and PhD in fluid dynamics from Indian Institute of Science, Bangalore. Dr. Chandrasekar started his career with IIT Kharagpur in July 1998 and moved to Indian Institute of Space Science and Technology, Trivandrum in July 2009. Dr. Chandrasekhar's research work is in the area of mesoscale modeling, data assimilation, land surface processes, and land atmosphere interaction. Dr. Chandrasekar was awarded the Astronautical Society of India Award for the year 2014 in the field of space sciences. Sir, with this brief introduction, I welcome you, sir, for the lecture. Over to you, sir.
Yeah, good morning. I am already sharing the screen. I mean,
can you see this? Yeah. Yes, sir. Yes, sir.
Okay. So, good morning to all the participants. So, today I'll be talking on atmospheric satellite sounding. So, this is going to be different from what you were taught yesterday and the first session of today. Yesterday, you were given talks by Dr. Balram Rao, Dr. A.K. Patra, and Dr. T.N. Rao on various aspects of radar probing of the atmosphere, including the ionosphere. And Dr. T.N. Rao spoke about radar meteorology and how the radar is a very, very important tool to study the various atmospheric phenomena. Today, the first session, you had a fascinating presentation by Professor B.N. Goswami on the various aspects of clouds, precipitation, and he also shared with you his experiences as far as his cloud seeding experiments, which were conducted when he was heading the Indian Institute of Tropical Meteorology, Pune. So today I'll be talking on atmospheric satellite sounding. So essentially, this topic will dwell on how do we determine the temperature profiles, the air temperature profiles from satellite data, and how do we determine water vapor profiles from air temperature data. You will agree with me that these are the two most important fluid parameters as far as atmosphere is concerned, and we will study some theoretical background as to how this theory is being used to actually obtain. What is the philosophy behind this retrieval of temperature profile from the satellites? What is the theory and the philosophy behind retrieval of water vapor from in the atmosphere from satellites? So most of the material in this presentation is taken from this Remote Sensing Applications Meteorology Satellites by Paul Menzel from University of Wisconsin-Madison. So the outline of the talk will be, I will introduce to you these concepts of flux, irradiance, intensity, radiance, and all. So because your earlier lectures, yesterday's lectures were dealt with related to radar, and today morning with the cloud. So these are all these radiation concepts you wouldn't have known. So I will just briefly discuss about them. Then this concept of reflectivity, absorptivity, transmitivity, and emissivity. Then solar radiant flux and solar irradiance. Then we will briefly touch upon Planck's law of blackbody radiation. Then BS law, it's also known in literature as BS-Lambert's law. And we'll also see, discuss about Schwarzschild equation. Then spectral solar radiation, irradiance at the top and the bottom of the atmosphere. That will actually tell you what are the various constituents of the atmosphere that sort of absorb the incoming solar radiation. Then we'll also discuss in greater detail the atmospheric absorption of thermal radiation. Thermal or terrestrial radiation is basically the radiation from the Earth atmospheric system, and what are the various constituents of the atmosphere that absorb this terrestrial radiation, which is typically in the long wave part of the electromagnetic spectrum, typically from 4 micrometer to 100 micrometer. Then we will discuss about the radiative transfer equation, and we will take up the simple case of no scattering, and essentially we will talk about how in the infrared part of the electromagnetic spectrum one can retrieve temperature profiles and water vapor profiles. What is the philosophy behind this? And then we'll also briefly dwell into the difficulties in retrieving this temperature and water vapor profiles. And then I will mention again very briefly what is the microwave form of the radiative transfer equation and how do we sort of retrieve temperature profiles using the microwave part of the electromagnetic spectrum. And what are the advantages and disadvantages, if any, of using microwave radiation vis-a-vis the thermal radiation. Next slide. Can you all see the slides? Can I change the slides? Yeah. So now this is slide number 3, flux, irradiance, and intensity. So the first thing is we have to define what we mean by a radiant flux. Radiant flux or radiant power is basically the power or the rate of flow of radiant energy. Now basically you will see in subsequent slides. So the radiant flux from the sun is the source of all energy for the Earth atmospheric system. We all know that. So it is of the order of the radiant flux from the sun is of the order of 10 to the power of 26 watts. 3.9 into 10 to the power of 26 watts. That is the amount of energy coming out from the sun. So typically the unit of radiant flux is watts. That is basically energy per unit time, joules per second. So sometimes we also talk about basically instead of talking about radiant flux, we talk about spectral flux or spectral power. So spectral, the moment we use the terminology spectral as before any of this concept like flux or power, then spectral is a connotation used only per unit wavelength or per unit frequency. So when I say spectral flux or a spectral power, what I mean is a radiant flux per unit frequency or per unit wavelength. In most situations, we normally use per unit wavelength. So the unit of radiant flux is watts. So the unit of spectral power or spectral flux is simply watts per nanometers or sometimes watts per micrometer, depending on how it is more convenient to use either of them. Then we have this concept of irradiance, which is also a very important concept. Irradiance is flux of the radiant energy per unit area striking a surface. So basically, so when I said the radiant flux of coming out from sun is something like 3.9 into 10 to the power of 26 watts. And so one can think of what will be the irradiance of solar radiation which emanates from the surface of the sun. Now the surface of the sun, the visible surface of the sun has a certain radius. Suppose it is, if you consider that as r suffix s, which is the radius of the sun, then 4 pi r squared is going to be the surface area of that visible part of the sun's surface. And so the radiant flux, which is 3.9 into 10 to the power of 26 watts divided by 4 pi r squared, where r is the surface radius of the visible part of the solar spectrum of the sun. So that will give you the irradiance. So irradiance is simply the flux of the radiant energy per unit area that is striking a surface. So the unit of irradiance is simply radiance per unit area. So it's watts per meter square. And again, we can also again talk about spectral irradiance. Spectral irradiance would mean basically irradiance per unit wavelength or per unit frequency, as I indicated before. Normally per unit wavelength is what is normally used. So the unit of spectral irradiance would be watts per meter square per nanometer. Now, both these concepts of radiant flux and these concepts of irradiance have nothing to do with the directionality of the flux. So it does not depend on the irradiance, does not depend on from which direction the flux of the energy is coming in. So is the case with radiant flux. But we have these concepts of radiation, the measures of radiation, radiant energy, for which directionality is very important. So one of this is the radiant intensity. So the radiant intensity is nothing but the radiant flux emitted, either reflected, transmitted, or received per unit solid angle. So the moment, suppose the moment I put per unit solid angle, then obviously it depends on the direction from which the radiant flux is approaching the given surface. Okay. So this is highly directional, and obviously the radiant intensity has a unit of radiant flux per solid angle. So it is watts per steradian. Again, we can talk about the concept of spectral radiant intensity. Spectral radiant intensity would be nothing but the radiant intensity per unit wavelength. So that units of that would be watts per steradian plus per nanometer. The next slide. This is another very important concept called radiance, and like the radiant intensity, the radiance is also a quantity which depends on the directionality. So obviously the per unit solid angle will come into play. So the radiance is the radiant flux emitted, reflected, transmitted or received by a given surface per unit solid angle per unit projected area. So in effect, the difference between radiance and irradiance is the following. While irradiance is the total amount of radiant flux that is received, okay, per unit area, irrespective of the direction from which the radiant flux is being received, radiance is highly directional, directional dependent. So it is a radiant flux that is received by a given surface per unit solid angle per unit projected area. And again, like the previous definitions of the radiation quantities, spectral radiance is nothing but the radiance of the surface per unit wavelength. So the radiance unit would be radiant flux per unit area, which is the irradiance, which is watts per meter squared. And then per unit solid angle will give you per steradian. So the unit of radiance would be watts per meter squared per steradian. And the unit of spectral radiance would be the radiance divided by wavelength. So it will be watts per meter squared per steradian plus per nanometer. Now, all of you are familiar with this concept of Blackbody. So Blackbody is a hypothetical body which is characterized by complete absorption of all incident radiation, and that's why we call the body as black. So whatever be the incident radiation, all the radiation is completely absorbed. So such a body which completely absorbs all possible incident radiation is what we call as a black body. And because it absorbs all incident radiation, so it will also has the property that it has the maximum possible emission of radiation in all wavelengths and in all directions. So in other words, the black body is a body which is a perfect absorber and perfect emitter of all radiation. So as I told you, this is a hypothetical concept. However, we'll see as far as the Earth's surface is concerned, as far as thermal part of radiation, that's the infrared part of the radiation is concerned, without loss of generality, we can assume that the Earth's surface to be a black body. A body which is not black is defined as gray, gray body. It's an imperfect black body in a sense that it doesn't absorb all the incident radiation. That essentially means it does not emit the maximum possible radiation in all wavelengths in all directions. So to that extent, it is not a perfect body like a black body. However, the gray body, so that means it only partially absorbs the incoming incident electromagnetic radiation. So what will happen? The part which doesn't absorb, it can possibly reflect it back. That is one way it can. So the gray body has another important characteristics that it has constant monochromatic properties at all wavelengths. So the properties of the gray body do not essentially change with change of wavelength. That's a very important characteristic of a gray body. So next we'll introduce to you very important concepts of reflectivity, absorptivity, transmittivity, and emissivity. Maybe this picture in the next slide will amply. So if you look at the left panel here, so let's say that I have a portion of some gas or something which can absorb. Okay, so let's say that r lambda is a certain amount of radiation that is incident on this. Okay, part of this radiation can get reflected. So we define r lambda as the reflectivity. Reflectivity is of any substance is defined as the ratio of the reflected radiation to the incident radiation. So r lambda is simply r lambda into capital R lambda divided by capital R lambda. So basically it is that part of the incident radiation that is reflected. So that we call as reflectivity. So whatever is not reflected will penetrate to the medium, and here it can suffer absorption, and whatever it is not absorbed, it gets transmitted. So this transmittivity tau lambda, we define as the following. We simply define it as that fraction of the radiation which is transmitted to the radiation that is incident. So that is where we define transmittivity. And what is reflected and what is transmitted, the remaining gets absorbed. So we have the definition of absorptivity, which is A lambda. So A lambda absorptivity is nothing but it is the amount of radiation that is absorbed to the total incident radiation. So now, if you can see from this concepts of conservation of energy, so it's very clear that the incident radiation is there, then part of that gets reflected, part of that gets transmitted, and the remaining gets absorbed. So obviously the that part which is reflected plus that part which is transmitted plus that part which is absorbed together will make up the total incident radiation. So that is what this tells you. So if I want to know what is that part which is absorbed, I should have knowledge of the incident radiation minus that part of the radiation that's reflected minus that part of the radiation that is transmitted. So from this, so if I know two of the three, either reflection or transmission, I will know absorption. If I know absorption and transmission, I will know reflection. If I know absorption and reflection, I will know transmission. So this is a very simple concept which is logical, and there is a very well-known law in radiation. It's called the Kirchhoff's law, which tells you that at thermal equilibrium, we have the any substance which is a good absorber also happens to be a good emitter. So this is also indirectly we defined when we defined a perfect black body. We said this black body is a body which absorbs all radiation that is incident on it, and we also said black body is one which has the maximum possible emission of radiation of all wavelengths in all directions. So anything which is perfect absorber has to be a perfect emitter. So in that sense, the absorptivity can be equal to what we call as emissivity. I'll just come back to this definition. So whatever I had discussed is all given here. Now the emissivity is a material property which is ranging from 0 to 1, which measures how much energy a surface can emit with respect to an ideal emitter. Ideal emitter is here the black body, which has got perfect emission. So the emissivity is going to be equal to 1 for a perfect black body. So emissivity is simply the ratio of the radiant energy flux of a body to that of a perfect black body whose absorptivity is unity. So as I said, if the absorptivity is unity, then obviously the emissivity is also unity for a black body. So emissivity of any property would be defined as the amount of radiant heat flux of the real body and it is compared with the radiant heat flux of a perfect black body. Like for example, to give you an example, as far as the Earth's surface is concerned, as far as the microwave part of the electromagnetic spectrum is concerned, the emissivity is not equal to 1. So the Earth surface does not act as a perfect black body in the microwave part of the electromagnetic spectrum. In fact, the emissivity can vary from 0.4 to 0.5 over land, and then it can vary depending on the wetness of the soil. It can vary, the emissivity can vary, and over the sea also the emissivity will vary and has a different value. Typically it's got a little higher value in the sea. It has a different value in the sea versus the land. So this is the concept of and then as I told you, we have this Kirchhoff's law. So basically again since for a perfect black body emissivity is unity, so the absorptivity also we can define it as E over E0, and thermal equilibrium emissivity will be equal to the absorptivity. And for a gray body, for a black body, emissivity is 1, absorptivity is 1. For a gray body, both emissivity and absorptivity are going to be less than 1. Okay. Okay, I'll discuss this figure a little maybe after a few minutes. So this is our Planck body radiance. So I will discuss that Planck body radiance. Okay, before that, okay. Now, as I told you, the source of the Earth atmospheric system, the source of energy is the sun. So the radiant flux coming out from the sun, which is the radiant power, this is the amount of energy which is coming out from the sun per unit time. So this has a value of 3.9 into 10 to the power of 26 watts. So as I told you, the visible radius of the sun has an approximate radius of 7 into 10 to the power of 8 meters. So 4 pi into r squared of this visible radius disk of the sun. So that will be the surface area of the visible disk of the sun. So the radiant flux divided by the surface area of the visible disk of the sun will tell you. So that's what I've done. Radiant flux I divided by the surface area of the visible disk of the sun, which is 4 pi into r squared, where r is 7 into 10 to the power of 8 whole squared. And numerator is the radiant flux, which is 3.9 10 to the power of 26 watts. So this value 6.34 into 10 to the power of 7 watts per meter squared. So this is the irradiance of electromagnetic radiation, which is passing through the outermost limits of the visible disk of the sun. Okay. So now we can actually use these values to estimate what is the total irradiance that is received at the top of the atmosphere, Earth's atmosphere. So for that, what we do is, so the solar irradiance arriving at the Earth, at the top of the Earth's atmosphere, can be calculated by using this concept that the radiant flux doesn't change from the sun. So I know what is the irradiance at the outermost limits of the visible disk of the sun. I multiply that with 4 pi into the radius of the visible disk of the sun. So that's what I've done here. So this is the irradiance multiplied by 4 pi into rs squared, where rs is the solar radius, which is 7 into 10 to the power of 8 meters. So this will give you the radiant flux, okay, at the outermost limits of the visible disk of the sun. Now this one, since the radiant flux is same, the radiant flux that is received at the top of the Earth's atmosphere also should be equal to the same, and that will be equal to what is the irradiance that is received at the top of the atmosphere multiplied by 4 pi into RES. RES is now the distance from the Earth to the sun, which is 1.5 into 10 to the power of 11 meters. So basically, so the radiant flux is the same. Radiant flux at the outer limits of the visible disk of the sun must be the same as the radiant flux that is received at the top of the Earth's atmosphere. So basically now the distance between the sun and the Earth comes into the picture as far as this distance RES is concerned, and that is 1.5 into 10 to the power of 11 meters. So I know this. So this is nothing but 3.9 into 10 to the power of 26. I know RES is 1.5 into 10 to the power of 11 meters. So I can easily find out what is the solar irradiance that is received at the top of the atmosphere. That has a value of 1380 watts per meter squared. And that is a very important parameter, which we call it as a solar constant. Now, if you look at a planet which is more distant from the sun, from the Earth, vis-a-vis the sun, let's say Mars, then obviously what will happen? So this right-hand side is going to be the same, which is nothing but the radiant flux at the top of, basically from the sun, which is like 3.9 to 10 to the power of 26 watts. And so the solar irradiance that is received at Mars planet would be less, because the distance between the sun and Mars is going to be larger than the distance between sun and the Earth. So from likewise we can find out, so the amount of solar irradiance that is received in all planets which are farther from the Earth, farther to the sun vis-a-vis the Earth, the solar irradiance being received are going to be less than 1380 watts per meter square. Okay. So their solar constant value for the various different planets which are farther are going to be less than 1380 watts per meter square. So concurrently, those planets that are closer to the sun vis-a-vis the Earth, like Mercury and Venus, they will have a solar constant that is higher. Okay, so the most important radiation law was proposed by Max Planck, which goes by his name, Max Planck's law of blackbody radiation. So here, this is the expression derived by Planck. This was in the beginning of the 20th century, for which Planck was given this Nobel Prize. So this is nothing but the radiation intensity, which is a function of wavelength and temperature. C1 is 2hc squared. H is the Planck's constant, which is a value of 6.63 into 10 to the power of minus 34 joule second. C is nothing but the speed of light, which is 3 into 10 to the power of 8 meters per second. So C1 is 2hc squared, and C2 has unit of hc by k. H is a Planck's constant, C is the speed of light, K is a Boltzmann constant, which is a value of 1.381 into 10 to the power of minus 23 joule per degree. So C1, these are all H and C are constant. C2, H, C and K are constant. So C1 and C2 have constant values that are given here. Okay, C1 is 1.19 into 10 power minus 8 watts per meter square plus radian. So obviously these are all radiance quantities. You can see watts per meter square plus radian plus. So these are all spectral radiance. So basically C2 has a value that is given here. C2 has a value of 1.43. Okay. So now one can express this Planck's law of, so what you saw here, now this top panel, so this is nothing but wavelength, and this is nothing but the blackbody radiance. This is Planck blackbody radiance. So which is plotted for 3 different temperatures. As I told you, this Planck body B lambda is a function of lambda and T. So for a given wavelength and for a given temperature, you have a distribution of the Planck's blackbody radiation. So for 700 Kelvin, which is so this is the Planck's blackbody spectrum. For 6000 Kelvin, this is that, and for 5000 Kelvin is this. So you can see from this figure, with lower and lower temperature, the peak of this Planck's blackbody radiance curve actually gets shifted to the longer wavelength. So this is actually given by what is known as the Wien's displacement law, which states that the product of lambda max into temperature is a constant, where lambda max is, this constant has a value 2897, when lambda max is defined in terms of micrometer and T is defined in terms of Kelvin. So that Wien's displacement law, so lambda max into T is constant, tells you that for larger the temperature, smaller will be the wavelength at which you will have maximum intensity corresponding to the Planck's blackbody radiance. So that is what it means. Now for the average surface temperature of the sun, which is 5780, so you can see that the Planck body radiance will correspond closely to 6000 Kelvin. So the maximum intensity, the Planck's radiance corresponding 6000 Kelvin, is around 0.5 micrometer. Now the x-axis is wavelength in micrometer, so you can see that 0.5 micrometer. Now we all know 0.4 to 0.7 micrometer is a visible part of the electromagnetic spectrum. So this is the Planck body radiance, black body radiance for sun, solar radiation 5780, and the maximum intensity is the peak intensity is close to 0.5 micrometer, which is on the blue-green region of the electromagnetic spectrum, part of the visible spectrum. Now, if you take the atmosphere, Earth's atmosphere, so it has, we can say that is a typical average temperature of 255 Kelvin. So this would be the Planck radiance for the Earth's atmospheric system. Now, so this goes up to 4 micrometer, from something like 0.16 micrometer to about 4 micrometer is the solar part of the spectrum, which we call as the shortwave radiation. And the long wave radiation is what corresponds to the radiation emitted by the Earth atmospheric system, which goes from 4 micrometer to about 100 micrometer. So what you get to see in this is there is no overlap between the radiation or the Planck body radiation distribution that is received from the sun, and the Planck body radiation that is now radiated by the terrestrial Earth atmospheric system. So, so these have very little overlap. So this radiation, terrestrial radiation from the Earth atmospheric system, is typically what we call as a long wave radiation, because this is completely in the infrared part of the electromagnetic spectrum. This radiation coming from the sun, we call it as a short wave radiation. So it has certain part in the visible part of the spectrum. It has also a part in the infrared of this part of the spectrum, and a very small contribution coming from the ultraviolet part of the spectrum, less than 0.4 micrometer. So this is the Planck's law, Planck's Blackbody radiance distribution. So when I fix temperature, it becomes a function of wavelength only. So it's possible for me to rewrite the Planck's Blackbody radiation in terms of frequency and temperature also. So then it assumes this form. So if I integrate this Planck's Blackbody radiance over all possible wavelengths from 0 to infinity, so b lambda t into d lambda, lambda varying from 0 to infinity, would be the same as the Planck body radiance in terms of frequency, is equal to integral of b into nu t d nu, and frequency varying from 0 to infinity. Okay. So one can either express the Planck's Blackbody distribution radiance in terms of wavelength or in terms of frequency. So there is another very important law, which is called the Stephan-Boltzmann law, that states that the irradiance of a black body is related to the fourth power of temperature. So let's say that if I know what is the irradiance of black body radiation radiated by the Earth's surface, then I can find out what is the temperature of the Earth's surface. So if I know the irradiance, I just have to divide by the Stephan-Boltzmann constant, which is given by 5.67 into 10 to the power of minus 8 watts per meter squared per degree minus 4, and then take the power of 1 over 4, then I'll get the black body temperature. So the Wien's displacement law, we have already told, lambda max into T is 2897, where lambda is expressed in micrometer and T is in Kelvin. So the radiative temperature of the sun surface is 5780. So if I substitute here 5780, so this comes close to 0.5 micrometer, which is in the blue-green portion of the electromagnetic spectrum. If I put 255 Kelvin, which is the typical radiative temperature of the Earth's atmosphere, if I put 255 Kelvin here, then lambda max comes near about 11 micrometer, which is in the infrared part of the electromagnetic spectrum. So the next very important law, we'll call this, this is the Beer's law. In literature, it's also known as Beer-Lambert's law. So let me go a little quickly. So this figure will explain it much more nicely. So let's say that we have a certain amount of radiation that is incident, I lambda, and it encounters an absorbing gas of, let's say, thickness dz. This is unit area, unit cross-sectional area. So this is, let's say that it is approaching this at some angle phi. So this phi angle we normally call as a zenith angle. Now this is the amount of radiation that is incident, and this is the amount of radiation that is transmitted. So obviously the amount transmitted is less than what is the amount incident. That part of the amount that is reduced transmitted is accounted for the fact that some of this radiation is absorbed by this layer of absorbing gas. So all this Beer's law tells us very simply that that the amount by which the incident radiation is reduced, which is di lambda divided by the incident radiation I lambda, is actually proportional to the number of molecules per unit area that are absorbing the radiation along its path. So it will depend on what is the height. So more the thickness, dz, more would be the absorption. It would also depend on the zenith angle phi. So zenith angle phi, this is a secant phi component will come. So if it is normally incident, so it's going to be absorption is going to be less. So if it is inclined, then obviously the associated cross-sectional area and the volume, associated volume is going to be larger. Rho is nothing but the density of the absorbing gas. K lambda is what we call as the absorption coefficient. Absorption coefficient is a function of the composition, nature of the gas that is absorbing, the composition of this gas, the temperature and pressure, and has units of square meters per kilogram. So this entire product basically becomes dimensionless. Secant phi nu is no dimension. K lambda rho into dz is dimensionless. So basically rho is the density, and this is unit cross-sectional area we are considering. So dz is the volume. This is mass per unit volume. So this whole thing is mass per meter square, and basically K lambda is going to have a square meter per kilogram. So the product becomes dimensionless. So this BS law, when I basically integrated from particular Z till top of the atmosphere, then I get this. So I get a relation here. So I lambda equal to I lambda infinity. So what it tells you is this is the initial radiation, and it undergoes absorption. Okay, the absorption coefficient is K lambda, and U is what we call as the density weighted path length. Okay, and so so the initial radiation gets depleted, and what actually emerges is I lambda because it suffers absorption, and this with absorption coefficient is K lambda, and U is basically called the density weighted path length, and U is defined as secant phi into integral Z to infinity rho dz. So this quantity K lambda U is also called as the optical depth, is a measure of the cumulative depletion that the beam of the radiation has experienced as a result of its passage through a layer, and it's called the optical depth. So K lambda U is called the optical depth sigma lambda. So the amount of radiation gets progressively depleted, and the amount of depletion is proportional to the exponential of the minus of the optical depth. So if you have very large optical depth, then obviously exponential of that is going to cause a large amount of absorption. So this BS law is a very, very important law. So if you have seen, so I have incident radiation I lambda infinity, and it suffers depletion of energy due to absorption. So whatever that amount by which it is depleted is basically your nothing but your di lambda, which was shown in the previous slide. And so what is getting transmitted is basically your I lambda, right? So if you see here, just you see the previous slide. So I lambda is what is transmitted. I lambda infinity is the initial, and this is the amount by which it is depleted, right? So basically what is transmitted divided by what is incident. I lambda by I lambda infinity is what we call as the transmittance. The transmittance tau infinity of a layer of gas lying above a level Z is given by tau lambda is equal to, this is basically what is transmitted radiation divided by the incident radiation, and the transmittance is given by exponential minus of this optical depth K lambda into U. So here we are not considering any scattering, we are just assuming only the depletion of the radiant energy due to absorption. So if there is no scattering, so basically whatever is, you have the incident and there is certain amount that is transmitted. So there is no scattering, there is no reflection. So as we have seen from conservation of energy, so we have to have absorptivity plus reflectivity plus transmittivity is equal to 1. Here there is no scattering, there is no reflection. So absorptivity plus transmittivity should be equal to 1. So absorptivity should be equal to 1 minus the transmittivity, which is the transmittance. Okay. So absorptivity is given by 1 minus exponential of my optical depth. So you can see here with increasing optical depth, okay, so this is going to go to 0, and the absorptivity is going to reach a value unity. So here, so when I say a gas is absorbing, okay, the absorption coefficient K lambda, as I told you, depends on several things like the composition of the gas. It depends on temperature, pressure, and other things. So to just give you an example, in the infrared part of the spectrum, 15 micrometer, CO2 has a strong absorption band. So whatever radiation that is emitted by the Earth atmospheric system in the 15 micrometer is going to be absorbed by the CO2 that is present in the atmosphere. So if you look at the absorption spectra of CO2, you will find that the maximum absorption is happening at the center, that is at 15 micrometer. Now, so at 15 micrometer, K lambda is so large that only a small amount of vertical extent of the atmosphere or the vertical extent of CO2 is adequate to absorb virtually all the incident radiation. That is all the terrestrial radiation here coming from the Earth atmospheric system. Whereas if you are not at the center of the absorption band, you are slightly in the wings. Okay, then at the wings, the K lambda, the absorption coefficient is not as large. So then I can have a large number of path length or optical depth over which I can expect complete absorption to happen. So at wavelengths away from the absorption band, a path length many orders of magnitude much larger than what was at the center of the absorption line would be required to produce noticeable absorption. Okay, so this is the basic idea. At the center of the absorption band, you need to have only relatively smaller optical depths or smaller path lengths for the gas to be the incident radiation to be completely absorbed. But if you move away from the center of the absorption line, if you go to the wing of the absorption line, so I can have many orders larger path length. Even then, I may to have noticeable absorption. So if I move away to the wings, then the absorption coefficient becomes less, and then obviously it needs to have much larger path length, mass weighted path length u in order to have the same impact of absorption. So when we come to solar radiation, the wavelengths of solar radiation, that is wavelengths whose wavelengths are from, let's say, 0.1 micrometer to 4 micrometer. So hardly any atmospheric emission is happening, because as we have seen, atmospheric temperatures, if you recall the Planck body radiance, which I just showed in one of the earlier graphs, so it clearly showed that there's no overlap between the shortwave radiation corresponding to 5780 Kelvin of the surface temperature of the sun and the temperature, radiating temperature of the Earth's atmosphere, which is 255 Kelvin. So the terrestrial radiation is from 4 micrometer to 100 micrometer, whereas the solar radiation is from 0.1 to 4 micrometer. And so there is practically no overlap. So obviously, so in the shortwave part, or in the solar, the wavelengths corresponding to the shortwave radiation, there is practically no emission of radiation from the atmosphere. The only thing which we have to consider as far as the incoming solar radiation is concerned is the absorption that can happen. So within 0.1 micrometer to 4 micrometer, what are the various gases that can absorb the incident solar radiation? Only the absorption which we need to consider. Emission will take place in the long wave part of the electromagnetic spectrum, that will be from 4 micrometer to 100 micrometer. So however, at wavelengths of the terrestrial radiation, emission is happening and absorption also is happening. Absorption are both happening in this infrared part of the electromagnetic spectrum. Okay, so how much of this terrestrial radiation gets absorbed along upward path through the atmosphere is described by the same BS law, right? So you can see the K lambda rho secant phi dz, and only thing is now, so earlier this incoming solar radiation means dz is considered, it is a negative z direction, so dz was considered negative. Now dz is considered positive. Okay, so as far as the absorption of terrestrial radiation in the atmosphere is considered in the infrared part of the electromagnetic spectrum, so one can use BS law like what you have used here. As far as the emission of radiation in the infrared part of the electromagnetic spectrum is concerned from the atmosphere. So one can treat because we know that's the infrared part of the spectrum, so we can consider the Earth atmospheric system to be a black body. So in that case, we can use Kirchhoff's law, which says that any good observer has to be a good emitter. So one can get an expression for the emission. So the emission would emitting of the atmosphere. I'm sorry. See, the Earth's surface is a perfect black body in terrestrial radiation, but the atmosphere need not. So basically, the amount of radiation that is emitted by the atmosphere will be equal to. So this is basically your emissivity, right? Emissivity will depend, will be a function of lambda. That is what it says. So the actual radiation emitted divided by the black body radiation, that is going to be my emissivity. So the amount of radiation that is emitted is equal to the black body radiance multiplied by the emissivity of the atmosphere which is emitting. So now if you assume Kirchhoff's law, the emissivity is the same as the absorptivity. I can write B lambda into dA lambda, and this dA lambda I can again use from my BS law because that deals only with absorption. So you have K lambda rho secant phi and dz. So B lambda is a Planck black body monochromatic radiance. So I got an expression for absorption, which is given like this. Absorption of the atmosphere in the infrared part of the radiation. Then I got an expression for the emission of the atmosphere, which is like this. So I subtract the absorption from the emission to obtain the net contribution of the layer to the monochromatic radiance passing upward. So as you see, this is the emission. This is minus of minus is plus. So B lambda into this is that part of emission. The absorption is minus L lambda into this. So basically I subtract absorption from emission. So I get this. So this we call at the Schwarzschild equation. This is a very, very important equation. And this will form the basis for our radiative transfer equation, which we will use to actually retrieve the atmospheric as well as the water vapor profiles using satellite observations. So the Schwarzschild equation is the basis for computation of the transfer of infrared radiation in the atmosphere. So in a very simple way, for a moment, if you assume we have an isothermal atmosphere, so K lambda, normally it's a function of temperature. And so if this becomes independent of height, because it's isothermal gas with constant K lambda, so it's possible to integrate this and you get this. So what this tells me is K lambda U is my optical depth, right? So when the optical depth goes to very large values, so this becomes like 1. And so what happens is L lambda, so 0 suffix would actually indicate that is the initial radiance. So what it tells you is this is exponential minus infinity, it goes to 0. So what it tells you is this L lambda should tend to B lambda as the optical thickness of the layer increases. Okay. So even though the real atmosphere is not isothermal, so it turns out that qualitatively this thing is also seen for real gases which are non-isothermal. So it tells you that for a layer of infinite optical thickness given by the Planck's radiance, irrespective of the value of the initial radiance. So that means for all, when you have infinite optical thickness, so what is radiating at, what is emitting from the top of the atmosphere is actually the Planck body radiance. So that means the atmospheric layer behaves like a black body. So that is what it actually means. So many times in atmospheric science, we normally convert the vertical coordinate Z into pressure vertical coordinate. because this is very convenient as far as the upper air winds are concerned, as far as the upper air temperature, upper air humidity and all are concerned. These are typically expressed at various pressure levels, and so pressure as a vertical coordinate is more conveniently used in atmospheric science. So this requires one has to invoke the hydrostatic equation. Hydrostatic equation is nothing but a balance between the vertically directed pressure gradient force and the gravity force, and basically what one can sort of what one can conclude from the hydrostatic balance is the vertical accelerations are very small and they can be ignored. So that is the essence of the hydrostatic equation. And one can define a mixing ratio of a constituent of a gas Q is equal to rho by rho A, where rho is the density of the gas and rho is the density of air. So like if you want to know what is the mixing ratio of carbon dioxide, I just have to find out what is the carbon dioxide density and divide it by the density of the air. Then I will get an idea of the mixing ratio of carbon dioxide. So we all know that the atmosphere is constituents are nitrogen, oxygen. These two account for something like 98% of the total atmospheric mass, 76% by nitrogen and 22% by oxygen. And the third most important constituent is your carbon dioxide, which has something like 400 parts per million, which in terms of percentage will come to 0.04. Now, as far as these three constituents are concerned, nitrogen, oxygen, and carbon dioxide, they are all uniformly mixed in the atmosphere. They don't show any variability of mixing ratio with respect to height up to a height of 80 kilometers. This part of the atmosphere up to 80 kilometers we call as a homosphere, in which the atmosphere is fairly mixed, well mixed, with most of this components, the most important dominant components which that account to something like 99%, having more or less constant mixing ratio with height. So we are not much interested in deriving the temperature profiles beyond 80 kilometers, that is sometime in the thermosphere. And obviously these, whatever I am going to discuss will not be of much use, because to determine the temperature profile, I need to look at a constituent of gas which is uniformly mixed. So unless the mixing ratio of that constituent of a gas which I am going to use, whose absorption characteristics I am going to obtain from the radiometer in my satellite, I'm not going to, my method which I'm going to describe is not going to work. So the first requirement for temperature profile retrieval in the atmosphere, so I have to be satisfied that I can only get temperature up to 80 kilometers, which by and large one should be satisfied, because that takes care of the troposphere, stratosphere, and the mesosphere also. Okay. So the optical depth is now defined in terms of pressure as a vertical coordinate as secant phi. Phi is the zenith angle, integral 0 to p. Q is the mixing ratio of the absorbing gas, and 1 over g. G is the acceleration due to gravity, and dp. So I've just used basically dp by dz is equal to minus g rho. That is a hydrostatic equation. I've just replaced rho involving q and rho a. The density of air dp by dz is equal to minus g rho a, and rho a is now replaced by rho by q. So you get this relationship, and so the integrand now becomes basically q by g. So if you recall, we had rho dz and secant phi. Secant phi has come out, so rho dz is nothing but so minus and minus cancels, so q by g into dp. Okay, so the optical depth is now defined like this in terms of pressure coordinate. Okay. So monochromatic transmittance is defined as the probability that a photon of wavelength lambda leaving the pressure level P will reach the top of the atmosphere. This transmittance is given by exponential of this. So this is nothing but exponential of minus of the optical depth is what it is in terms of pressure coordinates. So this figure tells you, this figure shows you actually the solar spectral irradiance versus wavelength. So the top one tells you what is the irradiance curve observed at the top of the atmosphere. at the top of the atmosphere, the initial solar radiation doesn't suffer any sort of absorption, but once it enters the atmosphere, and what is actually received the surface is given by this. So as you can see that at different wavelengths, there are absorption that's happening both outside the visible spectrum as well as in the visible spectrum. So the solar irradiance observed at the sea level. So the shaded areas represent. So this is again solar radiation is absorbed in the atmosphere by oxygen, oxygen molecule, oxygen atom, nitrogen molecule, nitrogen atom in the ultraviolet part of the spectrum, and there is also absorption by ozone, CO2 and H2O in the IR region. So so ozone has a so this is what you can see, and so this is the Earth atmospheric emitted radiance overlaid on the Planck function. So this tells you what is the you can see here at 9.6 micrometer in the infrared part of the spectrum. So you have absorption by ozone. You have at 6.3 micrometer you have absorption by hydrogen. At 15 micrometer you have absorption by CO2. So these are the three main absorption spectrum. Absorption lines. Ozone 9.6 micrometer, CO2 15 micrometer, 6.3 micrometer is water vapor. So these are the main absorption by the constituent gas for the infrared part of the spectrum. That is the thermal radiation. So this is atmospheric transmittance characteristics. So you can see this is for the whole spectrum. So again you can see at 6.3 the transmission is less because water vapor absorption is happening. At 9.6 at 15 micrometer transmission is less because of CO2 absorption. At 9.6 micrometer again the transmission drops down because of ozone absorption. Okay. So energy emitted from the Earth atmospheric system is called thermal infrared. So this I have told, which is absorbed mostly by the following gas: CO2, water vapor and ozone. CO2 absorbs infrared radiation in 15 micrometer, H2O in 6.3 micrometer, and ozone has an absorption band in 9.6. So these and all I have told you. So basically the atmosphere is relatively transparent from 8 to 12 micrometer. So which is called the atmospheric window region. And this is the region that is used to measure the sea surface temperature. So basically radiative transfer serves as a mechanism for exchanging energy between the atmosphere and the underlying surface and between different layers of the atmosphere. So infrared radiation emitted by the atmosphere and measured by the satellite sensor is the basis of the remote sensing of the atmospheric temperature structure. So the radiance that is leaving the Earth atmospheric system, which can be sensed by the satellite-borne radiometer, is the sum of radiation emission from the Earth's surface and from each atmospheric layer that is transmitted. So I have a radiometer in the satellite, let's say a passive radiometer. It just receives radiant energy in definite, what I should say, definite bands. Then the radiator in the satellite is made up of two contributions. One is the contribution by the Earth's surface. The Earth is radiating. So whatever the Earth is radiating and which the overlying atmosphere is allowing it to be transmitted, that reaches the sensor or the radiometer in the satellite. That is one contribution. Then second contribution comes from each and every layer of the atmosphere that is radiating and which the overlying atmosphere is transmitting so that it can reach the radiometer in the satellite. So the contribution comes from the surface of the Earth, which is transmitted by the overlying atmosphere and contributed by the atmosphere, which is transmitted by the overlying atmosphere. So this forms the basis of radiative transfer. So we'll consider thermal radiation, the infrared part of the spectrum. So emissivity is equal to unity. So the Earth's surface is a perfect black body. The upwelling radiation intensity for a cloudless atmosphere. So cloud we are removing because that makes our discussion simple. So the upwelling radiation intensity which will be received by a radiometer in the satellite is going to be given by, this is the left hand side. So this is the contribution by the surface. So one is so the temperature PS is the surface pressure, temperature of the Earth's surface. For that particular wavelength, you will have a Planck radiance. So that will be the Planck radiance for that particular wavelength corresponding to the temperature of the Earth's surface. So this is the contribution. This is the Planck radiance. If I multiply with the transmittance at PS, this tells you how much of this amount of blackbody radiance that is radiated by the Earth is allowed by the overlying atmosphere to reach the radiometer in the satellite. So this is the surface contribution by the Earth surface. Then I have summation over P. Now the atmosphere, if you look at it, is not a, so atmosphere, different layers of the atmosphere have certain temperature, and they correspond radiance that is received at the radiometer in the satellite is made up of a surface contribution for that particular wavelength plus an atmospheric contribution for that particular wavelength. And so this is the blackbody radiance corresponding to that temperature at that level of the atmosphere corresponding to that particular wavelength lambda. So you multiply this blackbody radiance with the emissivity, you divide the atmosphere into different layers of delta P difference in pressure. So what is the emissivity of that? So emissivity multiplied by this Planck radiance is going to give you the actual amount of radiation that is emitted by one particular layer having a delta P thickness, and this is the amount of radiation that is emitted by one particular layer. And if I multiply by the transmittance, that tells you this is the total contribution received by the radiometer in the satellite corresponding to that emission of that particular layer in the atmosphere, which is allowed, transmitted by the overlying atmosphere to reach the radiometer in the satellite. So if I were to sum it over different layers in the vertical, I will find out the contribution of each and every layer. And in terms of, so the first term is the surface contribution, second term is the atmospheric contribution to the radiance to space. So now, if I use Kirchhoff's law, emissivity at pressure is equal to the absorptance. Emissivity is equal to the absorptance. Absorptance is 1 minus transmittance. So here I am again ignoring scattering and reflection because this is thermal radiation. I can safely ignore scattering. So basically, E lambda delta P is the emissivity is nothing but 1 second. So you can see here I have the product of emissivity and the transmittance. So emissivity is equal to 1 minus the transmittance. That's what we say, because there is no reflection. So emissivity plus transmittivity is equal to 1. So emissivity is 1 minus transmittance multiplied by the transmittance. Now this emissivity is for that layer delta P. So that 1 minus the transmittivity of that layer, the whole thing multiplied by transmittance of P. So basically we are looking at this term other than the Planck radiance in this summation. So this is what we get. Now we have defined the transmittance is an exponential function, right? So tau lambda P is nothing but exponential of minus secant phi 0 to P K lambda Q by G into dP. So this is nothing but our optical depth, right? And when I say tau lambda P, it is from 0 to that particular P. When I say tau lambda delta P, it should change from, the limits should change from P to P plus delta P. So if I multiply these two, in the first term I have a limits from 0 P to P plus delta P. In the second I have 0 to P. So both have minus signs. So the product is going to give me, this limits are going to change from 0 to P plus delta P. 0 to P plus delta P is nothing but the definition of transmittance for P plus delta P, right? So the product of these two are simply the transmittance at P plus delta P. Now, then, so I have this term, right? So one is I have multiplied these two products. I got this as transmittance P plus delta P. Another thing is tau lambda P. So multiplying these two, I'm going to have tau lambda P minus tau lambda P plus delta P. So this is nothing but delta tau lambda P. So this product of these two terms just gives me minus delta tau lambda. So in integral form, if I replace this summation, so I get this upwelling radiance intensity for a cloudless atmosphere. This is the amount of radiance intensity that is received with the radiometer. This is the surface contribution. There is no change here. Now this summation I now replace with, okay, summation I have kept it like this. Now I will replace it with the integral here. So this is the Blackbody radiance, and this delta tau lambda, now I am writing it as d tau by dp, because we are dividing the layers vertically with delta p thickness. So basically delta tau will become the vertical variation with respect to pressure of the transmittance into dp, and the limits are from the entire atmosphere, from the surface ps to the top of the atmosphere. So this is the this is what is the radiative transfer all about. Now the left hand side is what I actually measure in the radiometer. Now this is the contribution by the surface, and this is the contribution by the atmosphere. Now let us see how to use this in our retrieving of the temperature. So we can also write it again in terms of Z. So then it becomes like this: the surface contribution plus the atmospheric contribution. Now again d tau by, instead of dp, it's going from d tau by dz. So instead of ps to 0, it's from z equal to 0 to z equal to infinity. So again I can write this radiative transfer in terms of height. So let us look at this. Assuming that I have an isothermal atmosphere where the density drops off exponentially with height. So let's assume that density variation is like this: rho equal to rho naught exponential minus gamma z, where gamma is a constant, and I'll assume k lambda to be independent of height. So that the optical depth, I can now write it as like this. Optical depth is like this. So I put k lambda as constant, so I pull it out of the integral. Rho is varying like this. So I can integrate this variation. So I get something like this. Now, so this is the optical depth, and tau is nothing but exponential of minus optical depth, right? So because I have d tau by dz, so it will be like d sigma by dz. So I get this. So if you, for a very simple density, exponentially varying density, so it turns out that if I substitute this value, so I get like this: di lambda by dz is given by this, okay, and so this is given by this. So this tells me d by dz of I lambda. So I want to find out which level is emitting the most detected radiance. So I'm assuming for a minute that the surface contribution is either known and can be subtracted from the left hand side. So I'm looking only at the atmospheric contribution and looking at which level, which Z is going to contribute the most if I have a simple analytical profile of the density variation. So it turns out that in order to find out the level at which is emitting the most detected radiance, that means this should actually be this should be assigned to d by dz of this should be assigned to 0, the extremum value. So you find out that sigma lambda is unity. So whenever the optical depth is unity, that is the level from which is emitting the maximum detected radiance. Now you can argue that this is based on a very simple exponentially density varying pattern, and also we have assumed that k lambda is independent of z, but it turns out that the observed radiance is not very different from this. Okay. So the observed radiance contains information about the temperature of the atmosphere. It also has information about the gaseous profiles of the atmosphere. That's what I was trying to tell. What is the mixing ratio of, let's say, CO2, and hence this will have the signature of the observed information content of the observed radiance, which is measured by the radiometer in the satellite. So is it possible for us, from measuring the amount of radiance that is received by the radiometer in the satellite, can we infer the temperature profile of the atmosphere? That is what is the issue. So what we do is we take one constituent of the atmosphere, which is uniformly mixed, whose mixing ratio is constant at all heights. So the most and this constituent should have very strong absorption. So the example which we are taking is CO2, which we have known has a very strong absorption for 15 micrometer. So in very simple terms, it is like this. Now I take one constituent which is very strong absorption in the infrared part, 15 micrometer, which is CO2. Now the amount of radiation that is measured by the radiometer in the satellite, I will measure it at 15 micrometer, as well as I'll measure it at not at the center of the strong absorption band. I'll measure it slightly in the wings at several different wavelength, which are both at 15 micrometer as well as farther from that. The whole idea is the following. Now, any radiation that is radiated by the lower portion of the atmosphere at 15 micrometer, 15 micrometer has the strongest absorption. So the idea is anything which is radiated by the surface layer or close to the surface, that part of the lower part of the atmosphere at 15 micrometer is most likely going to be absorbed by the overlying atmosphere before it's going to reach the satellite radiometer, and hence this will not make any contribution. The contribution, if at all, of the central part of 15 micrometer CO2 absorption can only come from the upper layers of the atmosphere, because there is very little part of the atmosphere above that to absorb the radiation. Okay, so in a sense, so if you are looking at the wings of the absorption band, not at 15 micrometer, but at wavelength which is like farther away, let's say 15.5 or 15.8 micrometer, then the K lambda, the absorption coefficient, is not very strong there. So obviously the path length that is required to absorb all the radiation may be actually be much larger than the entire vertical extent of the atmosphere, so that the lower portion of the atmosphere that is actually radiating in the wings of the strong absorption band may actually be able to reach the top of the atmosphere. So this is in principle the whole idea or the philosophy of temperature retrieval of the atmosphere. So the center of the absorption band, the contribution has to come from the upper layers of the atmosphere. The contribution from the wings of the absorption band can come from the lower layers of the atmosphere. So this is the essential philosophy. Obviously, I will need to have a constituent of a gas which is uniformly mixed. So its mixing ratio is known, its absorption characteristics are known. So I will know everything about the right hand side. So now the whole thing is, this is the equation. I have the surface contribution I have taken to the left hand side. So assume that I know the surface temperature, then obviously I can calculate what is the Planck Blackbody radiance for a given wavelength. Let's say wavelength is 15 micrometer. I know this is the measured radiance that is measured by the radiometer. So transmittance also I can calculate for a Blackbody. So this is a known quantity. Now so this quantity d tau by dp, right? So let us look at it, what it tells. Okay, in order to make our same thing what I told you more clearly, you can see here. So basically I have three spectral bands A, B, C. So it's slightly offsetted. 15 micrometer is the strongest absorption band of CO2. That corresponds to A, right? So you can see that so basically the d tau by dz, which is nothing but the weighting function. Now the weighting function is drawn, okay, at different layers of different pressure levels. So this is d tau by dp. So you can see at the center of the absorption band, strong absorption band, where K lambda is the maximum, the contribution is coming from the upper layers of the atmosphere, centered around 100 hectopascal, which is farthest from the strong absorption band. The weighting function has a maximum around 700 hectopascal. and at a wavelength which is intermediate between the center strong absorption and the wings intermediate band, the maximum of the weighting function d tau by dp is now somewhere at 300 hectopascal. Now our life would have been much easier if I measure at 10 wavelengths here, and each of these 10 weighting functions had no overlap, and each of the 10 would correspond to certain portions of the atmosphere. But the difficulty here is that the weighting function of each of this absorption band has a relatively thicker, extends over relatively larger portion of the atmosphere. And like for example, at 200 hectopascal, you have the contribution coming from A, you have the contribution coming from B, you have also the contribution coming from C. So there is just no one-to-one way of actually resolving and assigning each layer to each of these absorption bands, A, B, C. A doesn't have just a maxima over one particular layer, and the whole thing is extending only to a small vertical extent. B does have an overlap with A, C does have an overlap with B and with A. So what happens is the retrieval becomes much more complicated because of this overlap, and the fact we also have other issues. I'll just quickly tell you what it is. Okay, so this is the philosophy. We'll shortly discuss the difficulties with that. Now I'll come to water vapor profile. Now for temperature profile, what did we do? We took a constituent of the atmosphere which is uniformly mixed. Because it's uniformly mixed, its mixing ratio is known, and it has strong absorption in the infrared part of the spectrum, let's say 15 micrometer, right? And I know all the information, so I can calculate what is the weighting function. So once I know the weighting function in the right hand side, the only thing I don't know is B lambda of T at different pressure levels. So it should be possible in principle to invert, because the left hand side is known, the right hand side I can replace this integral by basically, see what is done is I have measurements of the radiance received in the radiometer at different wavelengths, both at the center 15 micrometer as well as several wavelengths. Let's say we have 10 values. So I have 10 values on the left hand side, but it turns out in general, so this 10 values in principle I can only obtain temperature at 10 levels in the atmosphere, right? And even if you assume, then it becomes a linear problem. The 10 levels are not, the coefficients which are the weighting functions here are not sufficiently narrow. They extend over a larger vertical depth. So each coefficient you cannot assign to a particular wavelength. So the contribution of each coefficient can come from not one but several wavelengths. So this makes the whole retrieval problem little more difficult mathematically. So coming to water vapor profile. Now once I get the temperature profile, okay, so I have the temperature profile. So earlier what I did, I took one constant in the atmosphere which is uniformly mixed, whose absorption coefficients are known. So I can find out the temperature of the atmosphere. Now having known the temperature, if I have a constituent of the gas whose absorption characteristics are known and which is not variable, whose mixing ratio is not uniform in the vertical, then I can actually find out what is the mixing ratio of this variable constituent of the gas of the atmosphere. If I know what is the temperature of the of the atmosphere, temperature profile of the atmosphere, if I also know what are the absorption characteristics of this gas. So this is what is done for water vapor retrieval. For water vapor retrieval, we first do a temperature retrieval, get the temperature. Now I take 6.3 micrometer, which is an absorption band of water vapor in the atmosphere in the infrared part of the spectrum. These absorption coefficients are known, K lambda. At the center 6.3 is known, as well as the wings it's known. So again, it's the same principle. Now we are not determining the temperature, but we are determining the mixing ratio of water vapor. So in principle, if I know the temperature profile, I use the absorption characteristics of a constituent which is non-uniform in the vertical to determine the water vapor profile. So difficulties in satellite remote sensing. So this is what I actually was indicating. The outgoing radiance arise from relatively deeper layers of the atmosphere. So I showed you the weighting function that's not confined to one. If you recall, if I take 200 hectopascal, so you have the wavelength, the weighting function corresponding to the wavelength A, which is at the center of the absorption band. It also has contributions from the other two areas. So the radiance observed within various spectral channels come from overlapping layers in the atmosphere. This is also I indicated, and are not vertically independent of each other. Then the measurements of outgoing radiance have errors. So because of these three regions, so the contribution is coming from relatively deeper areas. At one particular height, the contribution is coming from different spectral channels corresponding to different wavelengths. And then, of course, the outgoing radiance has errors. Because of all these things, there are inherent difficulties in retrieving the temperature profile. So there are other issues. This is an example of a Friedholm equation of the first kind, whose solution is now quickly. I will. So this is the same thing I'm writing. So these are actually, there are very different methods how to obtain the temperature profile. So quickly I will talk about the microwave part of the radiative transfer. Now, whatever I talked was the infrared part, the thermal radiation. Now, if I go to microwave, the first difference is the Earth's surface is not a perfect black body. Okay, so when I talk of the radiance emitted by the surface in the microwave region, so there is a contribution by the surface. So basically, this is the Planck radiance corresponding to the surface temperature multiplied by the transmittance, whatever is radiated by the Earth's surface in microwave, and multiplied by the, if I multiply it by tau lambda, that is the amount that is transmitted by the overlying atmosphere. But what is radiated is not the Planck radiance, because it's not a perfect black body. The emissivity is not equal to 1. So the emissivity is a portion of the Planck radiance. So basically, this is the surface contribution. And what happens is, because it's not a perfect black body, the amount of radiation. So what happens is, it doesn't radiate the maximum possible radiation. So that means, since emissivity is the same as absorptivity, that means it doesn't absorb all the radiation that is incident on that, right? So that means there is some amount of radiation that is reflected by the underlying Earth surface when it comes to microwave radiation. So this second term represents the emission contribution from the entire atmosphere to the surface. Now, this integral is now reversed from 0 to PS. Remember, it used to be PS to 0. We are looking at upward radiation. Now this T lambda is actually downward. Now this is the Planck radiance for different layers of the atmosphere. This is the weighting function integrated from 0 to PS, from the top of the atmosphere to the surface. So this is the contribution multiplied by the transmittance at the surface, then multiplied by 1 minus epsilon. 1 minus epsilon is what? Epsilon is basically the emissivity, which is the absorptivity. So 1 minus absorptivity is the reflectivity. So this is the radiation coming from the atmosphere in the microwave part towards the Earth surface, and what is transmitted and reaches the Earth surface if you multiply by tau, and the whole thing if I multiply by the reflectivity, that tells me that part of radiation. So I have some radiation in the microwave part that is reaching the Earth surface, which is actually reflected back. So the contribution by the surface is, one is whatever it's emitting, and that part of the radiation coming from the atmosphere which is getting reflected back. So in the infrared part, we had only to deal with this, and emissivity was equal to 1 because we assumed that surface to be a perfect black body. Here you have a second term coming in. So the atmospheric contribution has, of course, the same form: 0 PS to 0 B lambda D tau lambda. So this atmospheric contribution in microwave is the same part. So this is the additional term which comes in because of microwave. And because of microwave, the wavelength is longer. So this is my Planck radiance. And because lambda is larger, C2 by lambda T is much smaller than 1. So I can expand this 1 plus X. So if you expand this 1 plus X, then I have So you have the Planck radiance becomes directly proportional to the temperature. So that is one advantage of the microwave. So in terms of blackbody temperature, the radiance is directly proportional to the blackbody temperature. So because the radiance is proportional to the blackbody temperature, whatever this I lambda I can now replace by the blackbody radiance, blackbody temperature. So wherever radiance was there, I can replace by blackbody. For a fixed lambda, this lambda power 4 will get cancelled. All C1 by C2, these are all constant, they will all cancel. So I will be now able to get an expression like this involving not radiance but brightness temperature. Okay, so there is some algebra here. This downward transmitted radiance is given by this, which can be because if you use the basic definition of transmittance, this will go from P will go from basically. So this is just algebra. So if you do the basic definition of transmittance, so you get this. So why we are doing this is to just put it this microwave radiative transfer equation also in the same form. Now if you see this F lambda P, if there is unity, then it has the same form as that of your thermal radiation, except that instead of brightness temperature we write the radiance. That's the only difference. So this tells me the brightness temperature measured by the radiometer in the microwave part is contributed by the Earth surface plus two contributions come from the Earth surface. One is by the emission by the Earth surface. Another is that part of the radiation which is emitted down by the overlying atmosphere, which is reflected back. So that is that plus the emission of the atmosphere. So basically we write this form in the same way. So F lambda P is given by this. So there are advantages in the microwave part. One big advantage is it can penetrate non-precipitating clouds. So clouds, if you recall, when we discussed the temperature retrieval using thermal or infrared part of the electromagnetic spectrum, we assumed the cloudless atmosphere. We don't have to make that assumption now because the microwave can penetrate the clouds. So the one other problem is of the microwave vis-a-vis the infrared is that the Earth surface is not a perfect black body. So the emissivity is not equal to 1. So you can see that the emissivity values of Earth surface can vary from 0.4 to 1. So for a C, typically it's lower, 0.4 to 0.5, depending on things like sea salinity, surface roughness, sea foam, and other things. So there is also a frequency dependence as far as microwave is concerned, with higher frequencies displaying higher emissivity values. So like over land, the emissivity depends on the moisture content. The more moist the soil is, the lower would be the emissivity. So emissivity of dry soil is rather high. Emissivity of wet bare soil is like this. So it's lower, and sea is definitely much lower. So the advantage of microwave is that it can penetrate clouds, and so that is one big advantage. So that's all. Thank you.
Thank you, sir, for the fundamental talk on atmospheric soundings. Now the participants can put questions on chat. So no questions.
Okay.
Yeah, one question, sir. But Daniel Simon was asking that what does it mean physically by the optical depth? Is it same as optical depth, which is used as 2AS, a proxy in cloud thickness measurement? What is weighting function? These all are his questions, sir.
Yeah, okay. Weighting function is, if you look at the radiative transfer equation, I lambda is equal to the surface contribution, the contribution of the radiance that is in the radiometer coming from the emitted by the surface and transmitted by the overlying atmosphere, plus the second term. The second term was the contribution coming from different layers of the atmosphere. So in the second term, if you recall, we had integral Ps to 0, B lambda Tp. B lambda Tp is basically the Planck radiance corresponding to that particular wavelength lambda, corresponding to the different temperatures of different levels of the atmosphere. That was multiplied by d tau by d lambda. Now this d tau by d lambda is nothing but the weighting function.
So
Okay.
also he's asking about the optical depth. What
Yeah,
is specifically
optical depth, as I told you, is defined as basically your exponential of minus k lambda into u, and u was like secant 5, then you had the density rho and then dz. So effectively it is a measure of so larger the optical depth would mean larger would be the sort of depletion of energy in a sense. Like for example, I have a certain, let's say I have a gas which is has a certain absorption coefficient. It has a certain thickness. It has a certain volume. It has a certain mass. Now I have incident radiation. Now the BS law tells me that the amount by which this incident radiation is going to be depleted is going to depend on exponential of this optical depth. So optical depth is, in a sense, gives you a measure of how much this incident radiation is going to be depleted because of absorbing gases that are there present in the atmosphere.
Sir, Y.S. Rao was asking, what is the free software that we can use for the calculation weighting function?
Free software for calculating weighting function? No, that would, I mean, I'm not aware of any free software.
Sir, may Beer's law be applied for optical ray also?
No, wherever absorption happens, I think it is applied.
Okay, sir. Sir, Praveen was asking, my question is also in connection to the optical depth. How valid are the assumptions made in deriving the model? I can see it as a probably a first order model. Are there any recent improvements in the modeling?
No, as I told you, see, when we deal with the thermal part of the infrared part of the radiation, it is perfectly valid to assume that the Earth's surface is a perfect black body. I can take the emissivity to be 1 for the Earth, for the Earth's surface. So this is perfectly valid. But the one thing I have not considered is, as far as the thermal part of the radiation is concerned, the scattering or reflection is not going to be of any importance. So obviously neglecting them is also not a serious issue. The one thing which we have not taken into consideration is the cloud effects. When I discuss the infrared part of the electromagnetic spectrum. So I did not take into effect the cloud effects because dealing with them is a little more involved. So if we don't want to deal with the cloud effects, then we can go for the microwave part of the electromagnetic spectrum, where now oxygen is what I should say, the absorption coefficient, which has absorption around 50 to 57 gigahertz. And this is a microwave part of the electromagnetic spectrum. And oxygen is a uniformly mixed gas whose mixing ratio doesn't change with vertical height. And so the same principles that we use for retrieving the temperature profile using IR radiation can be used for in the microwave part also. When it comes to microwave, I can afford to ignore the fact that the clouds and other things I can ignore safely because microwave can easily penetrate them. However, the microwave has issues. As I was telling you, the Earth's surface is no longer a perfect black body. So I have to, and different surfaces. We know that the Earth is has bare soil, then it has forests, then it has a very wet soil, then it has ocean, then it has waters. So of different salinity and all. So the emissivity becomes rather hard to establish. So the uncertainty in the emissivity values can contribute to limitations of the temperature retrieval if you use microwave part of the spectrum. It takes care of the cloud effects, but it does not fully take care of the fact that the Earth's surface is not a perfect black body. So, yeah.
So the Abhijit Kumar was asking, what is brightness temperature and how to derive the brightness temperature from satellite?
Yeah, so that's what I explained. If you look at the Planck's Blackbody radiance, okay. So basically, if I have, suppose I have a body, it has some temperature T. Okay. Now this body is radiating. Now this body will radiate in all possible wavelengths, that is in all possible frequencies. And if the body happens to be a black body, then its radiance distribution curve will be exactly similar to what derived by Planck's. Okay. So now from the Planck's distribution law, if I can I invert and get the brightness temperature? Can I get the, because the Planck radiance is a function of temperature. For a fixed temperature, I can plot the Planck radiance for different wavelengths or different frequencies, right? So the question is, when we come to the microwave part of the spectrum, it turns out that if you recall, e power c2 by lambda t minus 1 was there. So for microwave, which is longer wavelength, lambda c2 by lambda t is, because lambda is in the denominator, c2 by lambda t is a small quantity. So e power x, where x is small, I can expand it as 1 plus x, right? So because it's small, I can ignore all the quadratic and higher order terms. So 1 plus x minus x is going to give me x. So that tells you that in the microwave part of the electromagnetic spectrum, the Planck radiance is linearly proportional to temperature. So in the microwave part of the spectrum, whether I talk of radiance, Planck radiance or temperature is one and the same, because both are related directly. For a given wavelength, you have a lambda power 4 dependence, which can always be sort of taken care. So that is why it was very easy for me to replace the brightness temperature. Brightness temperature is simply the temperature at which the body is emitting. That's all. So, like for example, I want to determine what is the sea surface temperature. So what do? I have a radiometer in the satellite which will measure radiations coming in the so-called atmospheric window region between 8 micrometer to 12 micrometer. Within this window region, the atmosphere is mostly transparent to all radiation coming from the Earth's surface, right? So this is not going to suffer any depletion or any absorption in this wavelength interval, wavelength window. That's why it's called the atmospheric window. Then whatever is received in the satellite in this wavelength interval is going to come only from the surface. And so whatever is received, it is radiated by the surface. So, so for different, suppose I have one particular wavelength, I substitute, because Planck radiance is a function of lambda and t, right? If I measure what is the radiance in the atmospheric window region, which is received by the satellite, and if I presume that the Earth is radiating in a black body, whatever radiance received is a Planck radiance, which is a function of lambda and t. I know what is the particular channel, spectral channel, so which has a corresponding wavelength. So once I fix wavelength, then I can, from the Planck distribution, I can find out temperature. That temperature which we derive is what is called the brightness temperature.
Okay, sir. Sir, Kalapu Reddy was asking, uniform mixed carbon dioxide gas and its absorption at 50 micrometer help us to retrieve temperature profile through weighting functions. And whereas with the using this T profile, we can estimate variable water vapors profile.
Yeah. Water vapor profile means, see, it is like this. Whatever radiance that is received, for a moment we'll assume that the surface contribution is known. It can be taken to the left-hand side. So left-hand side we have I lambda, right? And the first term on the right-hand side is surface contribution. If I take like thermal radiation, the Earth is radiating in as a black body. So if I know the surface temperature, the ground temperature, then I can calculate for any particular wavelength what is the Planck radiance for that. So that is known. So I can take the first term on the left-hand side. So then the only unknown is my second term on the right-hand side, which is an integral of b lambda dp and the weighting function. Now the question is, now b lambda, that depends on what? That depends on temperature, that depends on wavelength, that depends also on, so what does this tau depend on? Tau depends on the absorption coefficient. Tau depends on what is the density of the absorption, density of the absorbing material, right? Absorbing constituent. Now what happens is, when we determine the temperature profile, because it's uniformly mixed and I know the mixing ratio of carbon dioxide, I know all the absorption characteristics of carbon dioxide. The only thing I don't know is the temperature profile. Whereas when I want to retrieve the water vapor profile, okay, so I know, I use the temperature information. So I know B lambda Tp, I know. Only the weighting function I don't know. The weighting function now depends on what? Now I am taking a constituent which is non-uniform in the vertical, but whose absorption characteristics I know. So I know K lambda. The only thing I don't know is rho, which is the mixing ratio of the constituent of gas. So this profile I can find out. Just like I basically all these things are indirectly there in the right hand side integrand of that second term. One earlier I knew everything about the optical depth. The only thing I didn't know was the TP, the temperature of the profile. Now I know the temperature. I don't know the Q, mixing ratio, or the rho, the density of the absorbing constituent. I don't know. So if I know that, then obviously right hand side term I know, left hand side is also known. So I have nothing to find out, right? So what we do is we know the temperature profile and take another constituent of the gas which is not uniform in the vertical and then use its absorption characteristic to find out what is its distribution in the vertical.
Okay, sir. Sir, he has one more question. How microwave radiative bands are useful for what kind of atmospheric parameter profiles?
No, it can be used. Microwave is nowadays more commonly used than thermal infrared because it has a huge advantage. It takes care of clouds. So operationally, it's the microwave thing which is most commonly used because oxygen has strong absorption around 50 gigahertz, and again the same all the radiometers that actually provide you atmospheric temperature sounding. The most recent satellites, they all use microwave.
Okay,
So
sir.
microwave has replaced the earlier thermal infrared.
Okay, sir. No more questions.
Okay, thank you.
Okay, this session is over. Thank you for all your kind attention. Now the lunch break. Then we will be back by 2 p.m.